So in this video, we will be modeling the free fall of a basketball using differential equations. But before we start that, let's just do a recap on the last video. So we considered a differential equation of the form y prime is equal to ay plus b. And we showed that the solution to this differential equation, given the initial condition y of 0 is equal to y naught, is this. So if we can get a differential equation in this form right here, then we can just plug in the corresponding values a, b, and y naught into our solution right here. And then that would give us the expression for our function that we are solving for. So let's say that I'm standing atop an infinitely long building. So here I am, this is me, and I'm standing on top of this building and I'm holding a basketball, and at time t equals 0, I drop the basketball. And I'm interested in the velocity of this ball as a function of time. So my unknown function is v of t, and the initial condition, the velocity at time equals 0, is going to be equal to 0 because at time equals 0, that's when I release the ball. So like any physics problem, let's draw a free body diagram. So here's our basketball right here, and we know that it has a force going downwards of mg, and it has an opposing force due to air resistance that we'll model as a force that is proportional to its velocity. So we'll define it as a proportionality constant k times its velocity. And from Newton's third law, we know that the sum of the forces is equal to mass times acceleration of an object. So in this case, the sum of the forces in the positive downward direction would be mg minus kv is equal to ma, where a is the change of velocity with respect to time, or dv dt. So this is our differential equation that models the free fall of this basketball. And I recognize this as a first order because it only has the first derivative. So it's a first order differential equation. It's linear because it has constant coefficients. And because it has constant coefficients, we can put it into this form right here and then use this equation to get our actual solution. So I'm going to rearrange this equation right here. I'm going to rearrange it, and I'll write it like dv dt is equal to negative k over m v plus g. All I did was switch the order of these two guys and then divide through by m. So with this, we definitely recognize now that it is of the form y prime is equal to ay plus b. And we know exactly how to solve that from the previous video. So in this case, our a would be the coefficient in front of the v, which is going to be negative k over m, and our b is going to be g. So if we plug those corresponding values in, along with our initial condition, v of 0 is equal to 0, we can plug it into this equation and get our solution. So our solution, v of t, would be equal to v naught plus b over a, which v naught is 0, and b over a is equal to negative mg over k. So we have negative mg over k times e to the ax, which is negative k over m, t. Don't forget, in this problem, we're using v and t instead of y and x, but it all means the same thing. And then minus b over a, which is, again, negative mg over k, so this becomes a plus, and I get mg over k. So I can rewrite this in a more appealing form by factoring out mg over k, and I get mg over k times 1 minus e to the negative k over m times t. So this represents the velocity of our basketball at any time t. And let's say that you forgot this fact. Let's say that you didn't have the solution already written down. You could very well start from the differential equation that you derived from from Newton's third law, and the sum of the forces is equal to ma, and we can just integrate again. And in fact, let's go ahead and do that just so we can build up a little more practice. So if we start from this equation, I'm going to go ahead and multiply through by negative m over k in order to get this v by itself, which again will make things a little more simple whenever we integrate it. So if I multiply through by negative m over k, I get negative m over k dv dt is equal to v minus mg over k. And now I'm going to rearrange this into dv over v minus mg over k, and this is going to equal negative k over m dt. So now I can integrate both sides, and this gives me the natural log of v minus mg over k is equal to negative k over mt plus c. And now I can take the exponential of both sides, which gives me v minus mg over k equals c e to the negative k over mt, which means that v of t is equal to c e to the negative k over mt plus mg over k. And now recall that our initial condition was v of 0 is equal to 0 because the ball is starting from rest. So I can use that. I can plug in v of 0 equals 0. So v of 0 is equal to 0, which equals, I just plug it into this expression now, c e to the negative k over m times 0 plus mg over k, and this simplifies to c plus mg over k. So now I can solve for c, and since c plus mg over k is equal to 0, then that means that c must equal negative mg over k. So now that I solve for c, I can come back and plug c into this equation, and I get v of t is equal to negative mg over k e to the negative k over mt plus mg over k, which we can rearrange by factoring out mg over k into mg over k times 1 minus e to the negative k over m times t. And this is exactly what we got by making use of our solution that we obtained from the previous video. So you can see that you can derive a solution for an arbitrary form, and we can use that to automatically get solutions to our models that fit that form. Or if you forget or don't have access to that solution, then you can always rederive it yourself through integration like we just did. Either way, you will get the same function, like we just demonstrated with these two. But anyway, let's just think about this for a second. We were able to take a real applicable situation of me standing on a building with a basketball, and we were able to model that with differential equations, and our result will tell us the velocity of that ball at any time t. I personally think that's pretty cool. And if you guys agree, go ahead and leave a like, leave a comment, share with your friends, and meet me here for the next video. So thanks for watching.